Hello, chemistry. Well, we're going to be talking about measurements, trying to make our measurements as precise as possible and also as accurate as possible in this small video. Now, do you remember what this curved water line is called? With water, it's usually down like this, and so you got to read the very bottom of this curved water line. In mercury, it actually goes, we don't use mercury, but sometimes water will actually not adhere to the sides very well, and so it will be, when it's a plastic small graduated cylinder, so you have to read the top of it. So let's what is the name of that curved water line? It is the meniscus. Okay, the curved water line is called the meniscus, and yeah, I told you can remember it by remembering that men is cuss. Now I'll help you remember to spell it right. But it's very important that in all of our graduated cylinders, they're glass especially, that the curved water line, the meniscus, you read the very bottom of the meniscus when you're measuring volume. So what I'd like you to do is I'd like you to pause the video now, and I'd like you to really look at these and determine what is the bottom of the meniscus is about right here, okay? And I would like you to pick one of these measurements. In a little while we'll be analyzing this a little bit more. So go ahead and pause it and do that. Now we measure a lot of things with a little bit of uncertainty. That's because we have to estimate between the lines. Okay, this looks like it's about halfway, maybe it's a little bit more between these two lines, and so we have to estimate that measurement. I'd like you to know that every type of instrument, even digital instruments, have got some uncertainty in them also. The very last digit to the right is always estimated to the very best of the ability of that instrument and how it reads it. And in most cases, it's our eyes that are reading it, not the digital ones, but our eyes that are reading it. And so sometimes that uncertainty has to be reported certain ways. Anyway, so I'm sure that you got an idea of how you could read between the lines on this, but why? Well, that's because remember, all of these instruments that we have in our lab and everywhere else are all supposed to be replicas of another instrument somewhere else. And they're not perfect. They have some flaws. And also because there's a long distance between these, we have to estimate between them just because we want the most reliable reading possible. Okay, so what is the reading on this graduated cylinder? Well, let's look at the two lines involved. Okay, the bottom of this meniscus is between 3.5 milliliters and 3.4 milliliters. So we want to make sure that we read between the lines and that we go one more decimal place over. So our reading should go to the hundredths. And it's not going to be 3.5 something, it's going to be 3.4 something because it's got to be between these two values. So let's go ahead and look at a line here. This line right shows us a little bit above half. So I would estimate this one to be about 3.47 milliliters. Okay, now that should be no different, but you know what? Somebody might see that as 3.46 or 3.48. And so we can also show that uncertainty by showing that you can go up or down one more digit on that very last decimal, and this shows how far it could deviate and show the uncertainty of the instrument. So that's how we will end up doing that. So again, these are calibrated to tenths, so that means that your measurement will be calibrated, will be reading to the hundredth because you go one more decimal place beyond it. Now what if the meniscus was at the bottom of 4 here? Since these are still calibrated at tenths, it would have to be 4.00 because we go one more decimal place beyond the calibration of our instrument. Wait, let's go back to that for 1 second. That shows the precision of our instrument. Now, if I was using a big, huge graduated cylinder that was like a 1 liter one, you'd be estimating the tens on those. So, I mean, you really have to show the precision of your instrument, and you don't go beyond the precision of your instrument because then you are kind of lying. So, we have to make it the most reliable and the most precise as possible. Now, here is that example that we had on the very first page again, and notice that this is 22, 24, 26, 28. So gosh, it's just right right about at 28. So what were you thinking that this one was? I think it's about right on the line. Anyway, since these all represent ones, I've got to show that by going to the nearest tenth. Okay, so B is the best answer to choose from here. Quite often, students, they will say, hey, that's a hair above it, and they will go one more decimal place beyond what they're allowed to. And so you can't do that because that instrument is not that precise. Same calibration, same instrument actually, even when this picture was taken. Anyway, these all go by 1, so you have to estimate to the nearest tenth, so that's already knocking out a couple of these answers. Sometimes students, they will read below and above the line wrong, so make sure that you're recognizing that here is 19 and here is 20. And so the best answer for this one is a couple hairs below 20, which is 19.7. Now, we will talk more about these in class and practice these in class, and we'll be dealing with it tomorrow. Anyway, how reliable are your measurements? We want them to be right on the value. If it's 3.47, we want to be measuring 3.47. And yeah, you can be off just a smidge on that last digit. But when it is close to the actual value, we call that accurate. Okay, when it's the actual value of 3.47 or whatever that's supposed to be is accurate. And as you get further away from accuracy, your measurement is going further away from what it actually was. Now, so that's accuracy. Now, precision, they always say that that's exactness of your measurement. Well, that's what I was talking about if you use a graduated cylinder that's calibrated to the tens or to the tenths. Okay, if it's calibrated to the tenths, it's much more precise because each one of your lines or your calibration on the instrument represents a smaller quantity. Okay, now precision also is talking about repeating results over and over and over, the exact one or really close to it. So precision is talking about using a really precise instrument with very small calibrations, or it's repeating your tests and getting a small grouping that's really close together. What you really want is to be accurate and precise. Okay, so accuracy and precision again. Precision is the closeness of your trials, and accuracy is the closeness to the accepted value. So if you go and average all these, they're going to deviate because they're further away from each other, but they're going to go somewhere close to this middle here. So they're not very precise, but they're pretty accurate. Now these ones are close grouping, so that means that they are closeness of trial, so that means that they're going to be precise, but they're not close to that actual value, so they're not very accurate. Okay, and we also talk about percentage of error, percent error. That's what we do to see how accurate that our results are. And sometimes you're actually graded on your accuracy and your precision on some of your labs to see how well you do. And let's talk a little bit more about this. So now we've got 4 results are really close to the bullseye. So this is highly accurate and highly precise. This one is showing good precision because they're grouped together really close together again, but they're not accurate. Low accuracy. Now these are spread out all over the place. And since they're spread out all over the place, that means that they are not precise. And their average comes somewhere in here, so they're not very accurate either. In fact, it's low accuracy, low precision. But let's talk about values of how we'd actually see them if we were doing a lab. So you went and took the density of something here and you got some results. You got 2.70 grams per milliliter, 2.701, and 2.699. These are all very, very close grouping together, aren't they? Very close. And so you can see that these ones are close grouping, so that means that they're precise. Close grouping, they're precise. They're also very close to the actual value. So to even tell if something is accurate or not, you'd have to know, well, what is that actual value? Okay, and so these ones are both accurate and precise. Here's another one. Okay, now the actual value still is there, but this time your group got a 2.40, a 2.791, a 2.907. This is not a real close grouping. It's kind of spread out. So it's not very precise. And here's how they're showing it on the other diagrams. Not very precise because not a close grouping. But you need to know what is the average so you can compare that actual value to it. And it's really close to that. So this one is accurate, not very precise. And the last thing we'll be talking about is accuracy and error. We sometimes have to calculate our experimental error, and when we do that, we take the value that we should have got, which is probably from the periodic table, okay, or something that the lab gave you, and then with the value you got, and you find the difference of it, and you divide by the known value, the theoretical value. So in this case, a student measures the mass and volume of a substance and calculates its density to be that, 1.40 grams per milliliter. The correct accepted value on the periodic table reads 1.3 grams per milliliter. So what is the percent error? Well, again, we take the two values, the experimental error, which this is, you could put absolute value bars on here. You just got to find the difference of the two, which is going to be 0.1, and you divide it by the accepted value, which is 1.3, and once you divide that, then you will get 7.7% error. Not so bad. Okay, and that's it for this video. And tomorrow class we'll be talking about accuracy and precision. You'll have to know which is which in class. See you tomorrow.